Okay, so I wanted to show you one proof by induction and how it works. So I'm going to go through the example in the book and actually show you what it would look like if a normal person was actually doing a proof by induction. So they start you with the formula that you're going to prove, and these are generally formulas involving integers, and they go through when you would do this, when you don't want to do this, but they are supposing that what if you add up the squares, so 1 squared plus 2 squared plus 3 squared all the way up to adding n squared for any positive integer n, they would say that that equals n times 2n plus 1 times n plus 1 all divided by 6. This is a typical formula that you would actually use induction for, so it would be amazing to actually do a deductive proof to like show logically how that works, but instead we're just going to go through the induction process. So step 1, it would be silly if this didn't even work for n equals 1, and we need it to work for some number, so we're going to say we are going to show that it works for n equals 1. If it doesn't work for that, we're done. So for that to be true, it's the sum of the first square, so that would be 1 squared. Does that equal, and we're going to plug 1 in for n over here, 1 times 2 times 1 plus 1 times 1 plus 1 all over 6. And you actually need to show your steps. So this is 1 equals 1, 2 times 1 is 2 plus 1 is 3, 1 plus 1 is 2 over 6. So does 1 equal 6 over 6? And yes, it does. So we've shown the first step. It works for at least one case. Well, step 2 is to assume something. So step 2, we are going to assume, let me say again, show, step 2, assume that it works for some integer k. Now, k could equal 1, which is this step up here, so it's true for k equals 1. What you want to do is say, well, you know, what if it's any k you have? So if we're assuming, then now we know that 1 squared plus 2 squared plus 3 squared all the way up to k squared equals k times 2k plus 1 times k plus 1 all over 6. So that's the assumption. And then we are going to go back for step 3. And we're back to a show. So basically what we want to do is say, okay, if it works for this one, then it's also going to work for the next one, which proves it because let's say k equals 1. Alright, so we know that k equals 1 works. If k equals 1 works, if this is true, then we would say, well, k plus 1 would be 2. Alright, so it works for 1 and then it works for the next one. So if it works for 2, and then we have this step, then it's going to work for 3. If it works for 3, then it works for 4. You're starting with 1 where it works, and the next 2 steps let you say it works for everything after that. So your goal for step 3 is to basically show that if it works for k, let's say n equals k, then it works for n equals k plus 1. And what that actually looks like is you would take the sum of the first k plus 1 squares. So 1 squared plus 2 squared plus 3 squared plus dot dot dot. I'm going to put in plus k squared because that's what we had. Plus the next one would be k plus 1 squared. And we need that to equal this, but instead of a k, for every k, I'm going to put a k plus 1 in its place. I'm going to have to use the next line. So this equals, instead of k, we have k plus 1. We have 2 times k plus 1 plus 1. Instead of 2k plus 1, 2k plus 1 plus 1. Instead of k plus 1, we have k plus 1 plus 1. All over 6. This is your goal. You want to start here and get it to actually look like this. So one thing you want to note about your goals, because you're not actually allowed or supposed to work on both sides of a proof, on both sides of an equal sign, you want to work on one side to get to the other, is what does this really look like? So you can actually keep that in mind, because it's hard to imagine how algebraically you're going to do something and have it turn out like this. So note that k plus 1 is one factor, then you've got two other factors. So basically you need to end up with three factors on the top. The second factor, if you look at it, 2k plus 1 is 2k plus 2 plus 1. So that's really a 2k plus 3. K plus 1 is a k plus 2. So this is what I'm looking to get before I get to my last step. And this I would actually have on a separate sheet of paper, some kind of side note, because this is the last step. It is not your next step. We are going to work on the left side, not the right side of this. So, okay, again, what we're trying to show is that 1 squared plus 2 squared plus 3 squared plus all the way up to k squared plus k plus 1 squared equaled the right-hand side. So what I do know is the sum of the first k squares. And that would be the formula I started with. So I have that this is equal to k times 2k plus 1, and this is my assumption step, times k plus 1 over 6. And I'm going to add to that plus k plus 1 squared. Okay, so I've got two separate things. I know I need to get to one expression without the plus sign. So what I'm going to do is actually add the two fractions. So to get the common denominator, I'm going to multiply by 6 over 6. And then I'm going to write this as one fraction. So this is k times 2k plus 1 times k plus 1 plus 6k plus 1 squared all over 6. Okay, so I need to go from 2 on the top into 3 separate factors. And if I look at this now, I could try to work all of this out and then try to factor it. But I actually have a common factor right now. Both of these two expressions have a k plus 1 in them, so I'm going to factor them out. So this would equal, pull my k plus 1 out, and then over here on the left, I'm left with a k times a 2k plus 1. The k plus 1 is factored out. I'm left with the 6k plus 1, but just to the first power now because one of the k plus 1s has been factored out, over 6. And if you take a look back at our original goal, one of our factors was supposed to be k plus 1, and it's right there. So I just have to work with the inside of this expression. So I'm going to simplify that. So this is k plus 1. Then k times 2k is 2k squared plus another k, plus, and then I distribute the 6, so 6k plus 6, and this is all over 6. If I simplify further, I have k plus 1, and then I have a 2k squared. My k plus my 6k is 7k plus 6 over 6. Now I have a quadratic that I can factor, and honestly, I already know what it should factor into because I looked at it as my goal. If that doesn't work, then this proof doesn't work, and the formula is actually wrong. So this is k plus 1, and then when I factor this, it better be 2k plus 3 times k plus 2 all over 6, and I can check it. 2k times k is our 2k squared. Then we have a 4k and a 3k make up 7k, and 3 times 2 is 6. So it actually does work. So my very last step is I'm going to write my goal and then I'm done. So this is actually equal to k plus 1 times 2 k plus 1 plus 1. And you can see it 2k plus 2 plus another 1 is 2k plus 3. And then finally I have a k plus 1 plus 1 all over 6, and we are done. It is proved. So since it works for the very first one, we can assume that it's going to work for the second one, which means it'll work for the third one. So it works for all positive integers n. And that is a proof by induction.